Thank you for the introduction. Right, zero product structure of C-star algebras. This is going to be joint work, or it's about joint work with Eusebio Gardella, also from Gothenburg. And I want to start a little bit by motivating what we're doing. It's like a bigger project that we're working on, and the philosophy is somehow we want to understand how C-star algebras look like as purely algebraic objects. So forgetting that they are Banach algebras, forgetting about the norm, what can we say about them as rings, for instance? What can we say about them as algebras, as complex algebras? So we want to study both the C-star algebras, but also the maps between them. And then there are some results in this direction. So they are kind of classical. I want to start with that, and then I will get to the new stuff. So one classical result from the 60s is a theorem by Gardner, 65. And he studied when two C-star algebras are isomorphic as complex algebras. So forgetting about the norm, forgetting about the star, just as complex algebras. And he gave a very satisfying answer. Namely, if I have C-star algebras A and B, so throughout the talk, A and B are always C-star algebras. If I have a map between them, let's call it pi, and this is an isomorphism. Okay, and just to be clear, I don't mean a star isomorphism, I mean an isomorphism. So let me spell it out. It's a bijective, linear, multiplicative map. But not necessarily self-adjoint, star-preserving. Then there exists a star isomorphism, pi 0 from A to B, and a, well, what one could call a weakly inner automorphism from B to B. And that means it is implemented by conjugating with an invertible element for some E in B star star, invertible. Okay, and now what? Such that pi of A is beta applied to pi 0 of A. Okay, so in some sense, this answers everything that you want to know about isomorphisms, not star isomorphisms, isomorphisms between C-star algebras, because it tells you that they are all of a very simple form. They are a star isomorphism followed by an automorphism, so not a star automorphism on B, which is moreover implemented by an invertible element. So in particular, right, a consequence, a corollary of Gardner's theorem is that, well, A and B are actually star isomorphic, yeah, because well, there exists such a star isomorphism pi 0, and pi is automatically continuous. Right, so that's consequences of this result, because a priori we don't know if in just a bijective linear multiplicative map between C-star algebras is continuous. It may not be, but Gardner proved it is. So it's also in particular a automatic continuity result. Okay, so this tells you that well, the whole C-star algebra structure is already encoded in the complex algebra structure. That's one way of interpreting this result, and this is somehow, well, the direction that I want to go. So this tells me that the objects, the C-star algebras, are determined by their algebra structure. What about the morphisms, right? So here then the question is, let's call that question 1. Are homomorphisms, and that means linear multiplicative maps between C-star algebras automatically continuous. Okay, and that is an actual question. So that's an open problem. It's an open question. It's a very natural question that I think it's amazing that we don't know the answer to, I think. Of course, Gardner said the answer is yes if the map is also bijective. But of course, it's really a question about non-bijective maps. And I will tell you in a second that there is a result by Sakai that also says the answer to this question is yes if the map is surjective. So really, the question is only open for maps that are not surjective. And then the problem is that the image of such a map from A to B, well, it's a subalgebra, but it might not be a star subalgebra, and it might not be a closed subalgebra, right? So, and there lie the subtleties. I should tell you that yes, very good. I was so that was the next thing that I wanted to say. Namely, no, it's exactly. So this is the natural thing that which one should mention, that there are, of course, discontinuous homomorphisms from C-star algebras to Banach algebras. So they exist, and this was Garth Dales and Jean Estelle. How do I pronounce it? Estelle. Okay. Right. Yeah. Estelle in the late 70s proved this, I think, independently. So Dales. Yes. Right. So continuum hypothesis implies exists a discontinuous homomorphism from C of X. So X should be infinite, an infinite, let's say, compact metric space, to B. And now I said before A and B are always C-star algebras, not for this example. So this is just a Banach algebra. Okay. And it is actually a so-called radical Banach algebra, if you know what that means. So it's very far from a C-star algebra for sure. And okay, yeah. And it's not clear if one can, well, I mean, make B a C-star algebra or just embed it into a C-star algebra. So that's the problem. And as far as I know, but maybe Elias knows more, it's also unclear whether you can do without that. Yeah. That would show that there's some axiom. I don't know exactly what it was, but there are reasonable axioms, including and so on. Also, okay. So it's okay, so it's independent of ZFC. I see. All right, but nevertheless, this question here remains open, and I mean, I don't know, maybe it's also independent of ZFC. So. Berkeley math departments at some point sent out questionnaire to people asking for information about their experiences there and run the program. And some later time,
And then I listed people that failed to contact me. And they sent me, and I just like other people. Says, do I know how to find any? One of the people was who was on the faculty of the Berkeley Math Department at the time, and they could not find him.
Okay. Because he never showed up, or what? All right. Okay. Okay. Good. So let's move on. Right. So the theorem that I also already mentioned is by Sakai, and he actually, so in his book, he attributes it to Rickert, and it's a little bit difficult to date. I mean, kind of even before Gardner's result, if I did my research correctly. So they proved that the answer to question 1 is positive if the map is surjective. Okay, between C-star algebras, then pi is continuous, so it's an automatic continuity result. And that, of course, implies that the kernel of this map is a closed ideal. Right, and then if you mod out this kernel, you get a bijective map, bijective linear multiplicative map between the quotient of A modulo this ideal. And so, for instance, then with Gardner's result, B is star isomorphic to a quotient of A, right? So the algebra quotients, I mean, okay, anyway, yeah. So that's the result that tells me that the answer to Q1, question 1, is yes for surjective maps. All right. So there's also a very interesting result in this area by Barry Johnston from the late 60s that also shows that maps are automatically continuous if the algebra that you start with, the domain, is nice in the sense that it's non-commutative enough. It should not have any finite dimensional representations. Okay, so that's let me just squeeze this here. Johnson, 1969. Answer to Q1 is yes if A is unital and no finite dimensional irreducible representations. So for instance, if it's, I don't know, the Jiangsu algebra, UHF algebra, Kunz algebras, you know, simple, unital, non-elementary, they would all fall into this result here. And then any homomorphism to another C-star algebra is automatically continuous. Okay, so the problem really is, in some sense, about commutative C-star algebras. And so it's no coincidence that somehow the discontinuous homomorphism was really coming from a commutative C-star algebra. Yeah. So because this result of Johnson really says if you're far away from the commutative world, everything is fine, everything is good. All homomorphisms are automatically continuous. Okay, so this is about the structure of C-star algebras as complex algebras, and now we want to look at, well, the zero product structure, and that means we want to forget more. Oh, yeah. Uh-huh. I don't think so. I think the result of Johnson is as even to Banach algebras, if I remember correctly. Yeah, so it's
Does there exist a continuous homomorphism of UHF algebra, some other Banach algebra?
So I don't think so. I think, although now I just said it for homomorphisms between C-star algebras, I think it's actually results. It doesn't really, it's just about Banach algebras. So it's any map to a Banach algebra would also be automatically continuous, if I remember this correctly. Yeah. Because so the techniques that they use is this they call it ideal of non-continuity, and that is somehow some ideal that you construct from a homomorphism to some Banach algebra, and the key observation, or the key fact here, is that this ideal has cofinite dimension, so it's has finite codimension in the algebra. And then if the algebra has no finite dimensional irreducible representations, that can only happen if the ideal of continuity is everything. And I don't think that it matters anywhere that the target is a C-star algebra. Yeah. All right. So we want to forget more. We don't only want to forget now the star, right? That's what we did so far. We want to even forget part of the multiplicative structure of the multiplicative table. Want to only remember that part of the multiplicative table where things multiply to 0. Right, so that's less information, and then we want to ask if that is still enough to recover the C-star algebra. And somehow there is, of course, good reason to do such things. Very classically, it's known that there's a very close connection between isometries on certain objects in functional analysis and maps preserving orthogonality or zero products. So the first of these results is probably the Banach-Lamperti theorem that tells me that isometries on LP spaces, when P is not 2, are or can be described as maps between the underlying measure spaces that somehow map orthogonal parts of the measure space to disjoint parts to disjoint parts. And that was somehow the starting point. That was in the 30s, I think. And then a lot of similar results were proved all over functional analysis, describing somehow the close connection between being isometric, preserving the norm, and preserving some kind of orthogonality. Kind of orthogonality that we're looking at here now is zero products. So let me define this properly. We say a map between C-star algebras preserves zero products in it. I mean, almost insulting. So I apologize that I defined this, because it's exactly what you think it should do. If A times B 0 implies pi A pi B 0, right? So for all A, B, A. Okay, that's just that we're on the same page, because sometimes people might think of different notions of what it means that two elements in a C-star algebra are orthogonal. And there are actually different notions, but this is the one we want to look at today. It's in some sense the easiest one. And okay, so what is one type of map that definitely preserves zero products? Of course, homomorphisms, right? They do that. But there's another interesting class of maps that do that, and they are the so-called weighted homomorphisms. So let me define this. A map from A to B is a weighted homomorphism if there exists homomorphism, an actual multiplicative map. It's called pi 0 from A to B, and a weight. And the weight is an element in the center of the multiplier algebra of the target, such that, well, pi of A is given by multiplying this weight onto the image of the homomorphism, right? So for all A and A. Okay, and since this is in the center, I mean, I wrote it on the left, but I could equally have written it on the right. And then, well, let's check what I just said, that weighted homomorphisms preserve zero products. So that's a little the proof that every talk should contain comes now. So if pi is weighted homo, then it's pi preserves zero products. Okay, so let's say a times b is 0. Now let's look at pi of a times pi of b. Okay, so that's h pi 0a, h pi 0b. Okay, so now this is in the center. For instance, I can move this over there. Pi 0 is a homomorphism. So it's multiplicative. That is 0. And so it's 0. All right, so that works. So weighted homomorphisms also preserve zero products. And it's actually a very interesting class of maps that you know if you, for instance, know the definition of nuclear dimension, because the famous order 0 maps, CPC order 0 maps that show up in the definition of nuclear dimension are nothing but weighted star homomorphisms with a positive weight. And of course, they play a super important role in that area of the structure theory of C-star algebras. Okay, so now the guess here, or the big question is, under which conditions is a map between C-star algebras that now only preserves zero products, maybe it's not multiplicative, at least it preserves zero products, when is it automatically a weighted homomorphism? And that would be question 2. So, I mean, you could say, are C-star algebras determined by their linear and zero product structure? All right, so this would ask, does Gardner's theorem, which said that C-star algebra is determined by its linear and multiplicative structure, does it generalize? Okay, and concretely, what would I mean by this? So, given a map from A to B, which is bijective, linear, and then preserving zero products. So how would I formalize this? I would say that pi and its inverse preserve zero products, right? So that two elements multiply to 0 in A if and only if they multiply on the other side. Okay, that would say that the zero product structure in both algebras is the same. Given such a map, is pi automatically weighted homomorphism, and then actually it will be a weighted isomorphism? That's the precise question. If it's a weighted isomorphism, it turns out then isomorphisms by Gardner show you that A and B are star isomorphic. So in particular, this would imply that A and B are star isomorphic also in a very concrete way, similar to that result where we even have a structure result, like how do the isomorphisms between C-star algebras look like? That's somehow asking the same way, like how do the zero product preserving maps between C-star algebras look like? And that's the guess, that they are weighted isomorphisms. So the question in that generality is open, but I will tell you towards the end of the talk, well, our partial resolution of this question for a large class of C-star algebras. And then, of course, you could ask somehow the analog maybe of this question there. Somehow, when, under what conditions are linear zero product preserving maps automatically continuous? Even if they're not bijective, for instance. Okay. And given what we know about homomorphisms, it's kind of natural to assume, at least for the third question, surjectivity. Right? Because as long as we don't have an answer to question 1, we don't really expect an answer to question 3, because that's definitely more difficult. Sorry? Unless it's false. That's true. Yeah. This is my positive temperament, that I always hope that conjectures are true, and I never look for counterexamples, which is probably a mistake. But yeah, so I mean, all right. All right. Okay, so here comes a theorem together with Eusebio that or not answers these questions, but like somehow gives us an approach to answer them, and tells us a lot about the structure of weighted homomorphisms. All right, so if I have a map pi from A to B, let's say surjective and linear, then the following are equivalent. First one, it's a weighted homomorphism. So it's weighted apimorphism. Second, pi is semi-multiplicative. So that's an algebraic property, which means pi of AB times pi of C is pi of A times pi of BC for A, B, C, and A. And if you worked a little bit with CPC order zero maps, you might have seen something like this popping up there. So this is sometimes used in the, for instance, the functional calculus that you have for CPC order zero maps, that such a property here, such an equation holds. And it's very easy to see that a weighted homomorphism actually satisfies this. So it's this algebraic condition holds. And the third condition, which is also equivalent to that, is pi is continuous and zero product preserving. Okay, so this is good news. In some sense, it's an answer to these questions modulo continuity, because definitely here I'm throwing in the assumption that the map is continuous. If I assume that, then I know that preserving zero product is the same as being a weighted homomorphism, is the same as being semi-multiplicative. What is, I think, interesting, in my opinion, is that 2 implies 3. So a map that is only semi-multiplicative and surjective is automatically continuous. So this is also I mean, part of this is an automatic continuity result, and such things are typically very difficult to prove, because all the techniques that we usually use in C-star algebras, epsilon approximation and so on, you can forget about that. So if you want to prove continuity out of an algebraic condition, somehow it requires different set of tools than one usually uses. And so then the question would be, is it also equivalent to, say, the fourth condition, that is just zero product preserving. Right, and this we don't know. So that's this is unclear. But 1, 2, 3 are equivalent, and I think it very it clarifies what's going on. Now it gives us a strategy of proving that certain maps that preserve zero products are automatically continuous, because we might just try to prove that they are semi-multiplicative, and we will use this later to give some answers to question 2 and 3. Okay, I wanted to say a little bit about the proof. Okay. So some of the implications are easy, as I already said. From 1 to 2 is easy. From 2 to 1, the idea is easy. Namely, what do? You define a map. Let's call it alpha from B to B as follows. You just say alpha of pi AB should be pi of A times pi of B. Okay, and I can do that because pi is surjective, so everything in B is of the form pi of something, and I'm also using, for instance, Cohen's factorization theorem that tells me that everything in the C-star algebra can be written as a product of two things. That tells me that, okay, this defines alpha on every B. Of course, the question is, does it define it well? And for that, the assumption 2 comes in, right, to show that that's well defined. And then you show that that is actually a multiplier, so a central multiplier. So I'm thinking here of multipliers as maps, module maps from B to itself. And then you can check that if you compose my map pi with alpha, it becomes multiplicative, so that there will be my pi 0. And this is the weight, or it's the inverse of the weight. So this is the idea, but of course, the technical difficult part is to check that it's actually it works, that everything is well defined, that it's a multiplier central, and so on. Okay, so that's as much as I want to say here about this. Now, okay. Now I wanted to give an example, and I think I have the time for that, of a map that preserves zero products, is surjective, but not continuous. So it's a discontinuous linear surjective zero product preserving map. Let's call it pi, and it goes from L infinity to the complex numbers. Okay, and you may wonder why such a thing exists. I mean, it wasn't obvious to me when we started this, but it exists, and it's actually not, it doesn't depend on set theory, its existence. So how do you do it? Pick some point in the Stone-Check remainder of the natural numbers, and we think of this here, for instance, as continuous functions on beta n. Yeah, so it's the bounded sequences of complex numbers. Okay, and I pick something there, and then for a sequence, in L infinity, I set or define the support of x to be the natural numbers n, such that xn is not 0. Okay, it's a natural notion of support. I'm just picking out, I'm checking in the sequence of numbers, like at which coordinates do I have 0, at which do I not have 0. Okay, and then I define a set n. These will be the elements x in L infinity, such that T is not contained in the closure of the support of x. Okay, and this is well, it's a subset of L infinity. And then you can check that that is actually a linear subspace. This is maybe not entirely obvious, but also not super difficult to see. So
So your support is only actual method, and then you want to say that.
yeah. Right. And yeah, sorry, that wasn't right. The support is inside n, which I think as in here, and when I take the closure, I mean inside beta n. Yeah. Right. Yeah. Exactly. That will be one way of saying yes. Yes. Okay, so is it clear to everyone that this is a linear subspace? I mean, I have to check that it's closed under addition, yeah. But this is right. The point is that if I have two sequences x and y and take their sum, then the support of x plus y is contained in the union of the supports of x and y. No, it's not closed. Better not, because then I mean no, no, I don't think it's closed. But it's a linear subspace, and now I can find, I just choose, so that's I guess Hambanach or some axiom of choice. Pi that vanishes on n. So choose pi from L infinity to see well, not 0, so linear surjective, such that it vanishes on n. Okay. Okay, so far so good, right? And now, yeah, why is it why does it preserve 0 products? So that's what we should check, of course. And why is it discontinuous? So that was related to what you just said. I think the point is that n is actually dense, so it cannot be continuous. That would be the argument for that. Why does it preserve 0 products? So let me just put this here. All right, so if you have x times y 0, that means, all right, so the support of x has to be disjoint from the support of y. Otherwise, all right, at some so the product here is just component wise, right? So this implies support x intersected with support of y is empty, right? Otherwise, I would have some coordinate where x times y doesn't vanish. Now, property of different ways of seeing this, I guess. So it implies that the closures are also disjoint. So probably Elias has a way of seeing that. It's in some sense it's a property of, you could say, of the Stone-Check compactification of the natural numbers, or I mean, yeah, okay, but that implies that at least one of them lies in n. Okay, so pi of x or pi of y, one of them is 0. And I mean, we didn't come up with this example. I mean, this is kind of around in the theory of automatic continuity as like a standard example, but it applied to our setting, it gives us a discontinuous linear surjective zero product preserving map, which of course tells you that not everything is going to be as nice as in the multiplicative setting, right? Because in the multiplicative setting, Sakai's result told us surjective multiplicative maps are continuous. And this tells us surjective zero product preserving maps may not be. Okay, so things are definitely slightly more tricky. Yeah. The what? Right, we don't know. We don't know. Yeah, okay, sorry. You're right. This example shows that it's not. And I would show you in a second conditions under which it is. Yes, you're right, but you're right. It's yeah, exactly. Yeah. Good. Okay. So no. I was saying that is kind of so let's say it's an exercise. Otherwise, I think it's it should be easy to see that n extends. No, but
infinity functions with finite support, right? And they converge and L infinity functions be supported everything. Oh,
yeah. Right. Okay. Right. It's all right. So I have 10 minutes or not even. So let me tell you about some new stuff also. So here's a central notion. We say a C-star algebra is zero product balanced if the following happens: if the difference between AB tensor C and A tensor BC, if this is in the span of simple tensors that multiply to 0. And everything this inside just the algebraic, it's an algebraic notion. Algebraic tensor product of A with itself. Okay. This looks or should remind you of the semi-multiplicativity up there. Right? It's what this property kind of tells you is if you have a map that preserves zero products, meaning that somehow it vanishes on such things here. If these two things are equal, then it will be automatically semi-multiplicative. So that's the definition is made so that that works. Right, and that's already the proof of this proposition here. If I have a map from A to B, which is linear, zero product preserving, and A is zero product balanced, then pi is well, semi-multiplicative. So if the map was also surjective, it's automatically continuous. Okay, so in some sense, we're picking out a property of the domain that ensures that preserving zero products implies semi-multiplicativity. And then with this theorem up there will lead to continuity, automatic continuity. So the question is, which C-star algebras are zero product balanced, and exactly the example up there shows L infinity is not. And actually, you can show that a commutative C-star algebra is zero product balanced. If and only if, well, it's a finite set, so most of the time not. Okay, and then so far that's not very exciting, but we show that there are many C-star algebras which are actually zero product balanced, and that's the theorem. If A is unital without one-dimensional irreducible representations, then A is zero product balanced. Okay. It should remind you of Johnson's result that I mentioned earlier. He had a result about unital C-star algebras that have no finite dimensional irreducible representations, showing that homomorphisms out of such maps as such algebras are automatically continuous. It's in the same spirit. It's even a little bit stronger because we only assume that there are no one-dimensional irreducible representations. And so an interesting corollary of that is if A and B, let's say, are unital simple C-star algebras, then A and B are star isomorphic if and only if there exists a bijective linear map from A to B preserving zero products. And it's actually what the corollary in particular also shows is that you have such a map from A to B, bijective linear, and it preserves zero products in one direction. It would automatically preserve zero products in the other direction. And the C-star algebras are going to be star isomorphic. So it tells us that, yes, the answer to question 2 is yes, under the assumptions of the theorem. So unital C-star algebras that have no one-dimensional irreducible representation, they are determined by the linear and zero product structure. For instance, simple unital C-star algebras. Okay, so that handles, almost all the C-star algebras. What is not covered by this is, of course, the commutative C-star algebras, and the example also shows that something weird happens then. And well, as far as you stay away sufficiently enough from commutative C-star algebras, things are going nicely, and the zero product structure determines the C-star algebra. So that's everything I wanted to say. Thank you.